is lymph flow through the lymph nodes slowed? How is it achieved?
Is it muscular pressure?
We slow down lymph flow through the lymph nodes so we can sample what's going through. We slow it down. How do we slow it down? What about it? Yeah, there are more afferent vessels into and efferent, so they have to slow down. That way, the cells within the lymph nodes can decide what to move, filter out the lymph. Lymphatic capillaries, how are they similar to blood capillaries? How are they different? Let's start with the similarity. It's something similar. How thick is it? Thin. How many cells? One cell layer, similar to the blood capillaries, right? But how is it different? Sure, the contents makes a difference, okay? Permeability, which one's more permeable? Lymphatics are more permeable. How is this achieved?
Overlapping?
Yes and no. So they don't actually have valves. But there is something. Access. Overlapping what? The cells which act as valves, right? So there's no valves within the capillaries on the surface itself, so they'll let stuff in, but they won't let anything out of the capillaries, right? And what kind of stuff will they let in? Is it just oxygen, CO2, glucose, like our blood capillaries are? Proteins go through, debris, including cells as well. Even lots of cancer cells, we talk about how they spread because of this porous nature of the capillaries. They can easily go into the capillaries and then spread throughout. Another thing is these are also one way. There is nothing pushing anything from behind. They kind of start the process of the capillaries. Hence they also have to think. Where does lymph flow? What about how does it? Is it a closed circuit? So if the cells in the lymph, can it stay in the lymph throughout its life, basically, keep flowing? Right, so it's a one-way open circuit. Where does it? So we talked about the starting point, the capillaries. Where does it go? They'll go back. They'll go into the bloodstream, right? Connects to the bloodstream. Where does it connect to the bloodstream?
The venous system?
Yeah, whereabouts?
The liver? No, not the liver.
Yeah, with the two subclavian veins and the internal jugular vein. So for those of you who are lab, we saw that landmark. Of course, we didn't. We'll see it on Monday. But that's where they meet, right? Is it half and half, drainage-wise? No. What are the two vessels that drain? What are their names? Thoracic duct and the right lymphatic duct. So let's ask it this way. Lymph from the neck, where does it go? Using what of these two? The right side of the neck, sorry. Showing it, but it's it. Right lymphatic duct, left neck, thoracic duct, left leg, thoracic duct, right leg, thoracic classic as well, right? Where is the boundary to the right lymphatic? It's just the half of the head, half of the chest, and the right arm. Everything else is called the thoracic. Good. Now let's see. What is transported by the lymphatic system? What are some things that are transported? So where is the collection of these lymphatic capillaries from? What is it collecting? It's interstitial fluid. Once it's collecting interstitial fluid. Fluid, we talked about how in the arterial side of blood capillaries, fluid escapes. On the venous side, it comes back, but it's not the same. Right? There's some that escapes and not comes back directly into the venous. Right? Lymphatics will remove that. Okay. They'll also remove proteins, and you mentioned the plasma proteins. Proteins also. One more thing about a specialized lymphatic capillary found somewhere else. It has one main function. It's not really to take interstitial fluid. It's in small intestines. Again. No, that's a good point where we have lymphatic, that's lymphoid tissue in the small and large intestines, mostly small, yeah. But it's not for the capillaries, lymphatic capillaries. They're called lacteals. Those are lymphatic capillaries. What's their specific function in these small intestines? That's where they're found. They absorb the digested fat. Okay. Everything else on the small intestines, digested stuff, where will it go first? To the liver, right? To the blood, to the liver. That is fats, and then to the lymphatic first, then it will join. Same way with every other part. So it's really the thoracic blood on the left side, right? Those are the big ones. We want to make sure we still have that in mind. What's the proper name of the structures we non-scientifically call it tonsils? That's the other one we don't call it. It's another non-scientific. It's the palatine tonsil. What's the scientific name for the adenoids? Pharyngeal tonsil, good. And we have one more tonsil.
The lingual.
Lingual tonsil. Where's the lingual tonsil found? Back of the base of the tongue. Yeah. It's back of the palatine, soft palate. It's the palatine tonsils. Adenoids are actually the nasopharynx, and the pharynx is the gullet that connects the back, the tube that connects the nasopharynx, oropharynx, and the larynx, and the esophagus. Right? What are Peyer's patches?
Clusters of lymphoid nodules
Where are they located?
beneath the epithelial lining of the intestines.
Yeah, it's the intestines. Okay. They are lymphoid tissue or lymphoid nodules. It's allocated in the small intestines. Because do we have bacteria in our intestines?
Mm-hmm.
Yeah, normal flora, they're fine in it. We don't want them getting into what they cause infection. Okay, so let's also remind ourselves, we talked about 3 types of lymphocytes broadly over the 3 types. T lymphocytes, B lymphocytes, and the NK. What does NK stand for? Natural killer cells. So we'll talk a little bit more detail about these. Okay. So our immune system we can categorize as 2 major divisions. Okay. We say innate and non-specific. So anything, it doesn't matter what type of bacteria, it doesn't matter what type of virus, it doesn't matter what cells, it tries to capture them, destroy them. We'll talk about how it allows or blocks them. Right? while adaptive or specific, that involves our T cells and B cells. Okay, it's targeted to a specific antigen. Okay, we generally say as line defenses, the non-specific will be first and second line defense. Okay, first line is to preventing things from entering into our body. Doesn't matter what type of bacteria, our skin will try and prevent it from entering. Right, that's a nice visualization for a barrier. Okay, we'll talk about that. And then secondary, it's gone into our body, but again, non-specific, like the NK, natural killer cells. What do they destroy? It's virus-infected cells and cancer cells. Well, specific is a very targeted response to a specific antigen. Okay, so particular threat. And it's generally after exposure, right? And it depends on the lymphocytes, the B and the T lymphocytes here. Generally all these are, right? So let's talk about the non-specific, right? So we're going to talk about types, physical barriers. That's going to be first line. And then once they have entered these other ones, 6 of them, is going to be non-specific. Okay? What do you think phagocytes do? Eat. Yeah, there'll be macrophages and so on, right? We'll talk about the natural killer cells. We'll talk about the interferons. We'll talk about the complement system. It's a bunch of proteins. It's very similar to our clotting, our coagulation, most specifically. It's a cascade. And then we want the final side. And then inflammation and fever, again, is non-specific. It's trying to promote our immune system to segregate for inflammation, fever, for things to move, metabolism rate. Okay, so non-specific, right? And this is also called our first line defense. These are physical barriers. It's not just our skin. It's our lining too, because even though the air is within us, it's considered not in us, hasn't passed through and got into our blood, into our tissue. Okay? So all this digestive tract, if it's remaining in the lumen, it's still not in our body, within our body, in our body. Okay? So any of that, so epidermis, mucous membranes, and even the secretions. For example, the stomach acid is also part of the system. Okay? Bacteria goes in, there's always bacteria in the food we eat, and hopefully not a lot, hopefully we still catch it. So the acid in our stomach will try and break that down and stop from entering our body. So skin also is slightly acidic. In our skin we also have keratin and we have sebum. What is sebum released from? Sebaceous gland, right? The main function of it was moisturize, but also has antimicrobial effect. Okay? Then our stomach, the acid as well as the enzymes found there, right? What we see of each other, it's mostly the proteins. Okay? Same thing with the bacteria too. There are proteins that make their membrane that could be destroyed by the enzymes as well. Okay? Mucus. It doesn't itself do anything to the microorganism, it just traps it. What moves it out? Cilia, right? Especially in our respiratory tract, you might see move it out. Most often we don't even notice, we swallow it. It's just when its amount is increased, it's when we notice that we're producing mucus all the time. Okay? So that will also help in the digestive tract as well as respiratory and urinary tracts as well. Even the urogenital tract. Saliva and tears have similar. Tears, it washes off things from the eye, right? It's to create a barrier to remove things from entering. Same thing with saliva. It has amylase enzyme, but it has antimicrobial and lysozymes in it to break down the organisms. How does this help? If somebody suffered with a UTI, yes, we may give them antibiotics. What else will we tell them? Drink a lot. Why?
Flush it out.
Yeah, so that will produce more urine. It will flush that tract, right? So that helps to And diarrhea and vomiting is kind of a reflex, it's trying to do the same. There's a lot of bacteria in our large intestines, diarrhea, there's gastritis, and vomiting. So these are physical barriers, it's trying to prevent things from actually entering into our body. This is part of our non-specific, doesn't matter what it is, right? Doesn't matter which virus it is, it's trying to prevent it from getting into our body. Then these ones will be considered the next line or second line, they're still under the non-specific. Phagocytes, these, again, cellular defense is the first line, right? So they're going to just swallow up anything that they recognize as non-self, right? We have some different types, right? We will talk about Kuffner cells. These are located within capillaries in liver. Okay, they're looking for bacteria, because liver will get blood from the digestive tract. So they escape the membrane, they escape the Peyer's patch. We try and trap them into the liver. Right? Then monocytes. What kind of cells are monocytes? Where are they found? Where are monocytes found? You said what? Blood, yes. I think blood. Yes, it's blood, right? What kind of cells are monocytes? White blood cells, right? Leukocytes. Neutrophils, what kind of things do they swallow up? Bacteria, any bacteria. Eosinophils, in the first line part. Parasites, right? What's another function of eosinophils? What about analogy? Yeah, it kind of reduces the allergic response. It's also receptive to later on when it's high throughout, then it actually starts increasing allergic response to it. But for now, it's an immediate effect. Right? So macrophages can also leave areas from its blood vessels, right? And then they can go into tissue. We'll talk about it through inflammation. We'll talk a little bit about their diabetes is when they leave the blood, squeeze through and get into the tissue. Because capillaries, normally do they allow blood cells to pass through them? Normal capillaries do not. Okay? When it's inflamed, that spaces between the cells become more pronounced and cells can pass through. Next one is natural killer cells, part of our lymphocytes. These fight against virus infected and cancer cells. Okay, what they're going to do is cause what's called apoptosis. This is programmed cell death. Okay, they do it in two ways. One, they put a little hole in the membrane, so water floods the membrane. Two, as I mentioned, I think I mentioned this Monday, they'll actually stimulate the lysozymes to burst open. What happens when we do that? They will start digesting from inside out, right? Lysozymes and digestive enzyme protein. Right? So I haven't put it here, so you may want to add it. Oh, it is here. Against cancer cells and virus infected cells. Perforin is the one that forms those little holes in the. Next is interferons. Interferons is pretty cool, I think, right? It's released by virus-infected cells, but it's not going to do anything for the virus. What is different about viruses and bacteria? What are some differences you might think? Yeah, that's one very important difference, right?
Bless you.
Hijacks our cell, God bless you. It needs our cell. It uses the cell's mechanisms, whether it actually implants itself into our DNA and produce proteins, or uses our ribosomes, our rough ER, our smooth ER to produce what it wants, to replicate itself. So the cell is pretty much gone. It knows that. But what it does, it secretes interferon that warns neighboring cells. Okay, so neighboring cells were like, okay, let's put some guards now. Okay, so it's antiviral proteins that produce, which now prevent this virus from trying to infect the next cells. Okay, so it's pretty cool. Doesn't do anything for that infected cell, right? It will warn the neighboring cells that there is a virus around. For trying to protect yourself, use antiviral proteins. Okay. So next one is complement. That's the cascade. Okay, it's one leading. Once one is activated, it leads to the next, and so on. If you known about a blood test we sometimes use to see infections, just any infection, not specific to one infection. We know what blood test is, biochemistry. It's not a full blood count.
Will you check if there is like elevated white counts?
Yeah, sure. There's another test we do. This one will also tell us when we're treating them whether the infection is going up or down by the numbers of this. We could, but that's more serious. That's usually in the ICU. CRP. CRP, right? That's creatinine reactive protein. That's part of the complement system. Okay? So this acts as a chain reaction. What this does is multiple things. It's going to attract phagocytes to this area. It'll cause stimulate phagocytosis. It also will destroy membranes. It also puts what's called a membrane attack protein complex. This is big opening, again, much bigger than perforins. Perforins like a drill. This is like a gigantic hole with a sledgehammer. And then we'll also promote inflammation, which we'll talk about next. Yeah, put an image of it. So if you look at images, it's like a number of proteins that are activated as a cascade again, and then you result in this connection of, if this is a membrane, a big hole with membrane proteins being added to it. This will connect the external extracellular fluid with an intracellular. Inflammation. So there are 4 cardinal signs. Here I only put the non-scientific. Let me give you the scientific names as well. Okay. 4 cardinal signs of inflammation. You may have noticed this and never really realized it. Okay, so it's rubor, aloe, dollar, what am I mean? Tumor. Anyone recognize any of them? What about this one? The tumor. What is a tumor? It's enlargement, right? So swelling. Dollar is pain. Calor is heat, calorimetry, right? And then rubor is redness. So you might have seen all of that. You've seen something external and inflammation, right? You might have had a little pimple, kind of, it could be one you could notice. Any cuts, you might notice the redness. It feels warmer. There is so warmer, redness, it's swollen, and it's also tender and painful even without touching, right? The idea, what's the idea of inflammation? 2 main things. One is to stop things from moving out of the skin. Okay? So we don't want the bacteria, we don't want the infection to spread. So we segregate it. Okay? 2 is creates this giant target, right? Like a bullseye. Okay, here is something going on, everything will be attracted to the skin. Okay? So when that happens, we'll have quicker resolution, and then we'll also help the tissue repair as well. Right? So it will attract the immune cells, right? So temporary repair side slows down the spread as well as attracts the other immune cells to the skin. So these are the signs, cardinal signs of inflammation. Again, non-specific, doesn't matter what bacteria is it, the same kind of principle. Next is fever. Where is our body's thermostat? hypothalamus. So the reset is slightly higher. What's the normal body temperature in degrees Celsius? 37 is a nice middle point, so 36.5, 37.5, excellent. So it'll just set it a little bit higher. Okay? So what it does, why would we set it higher? What's the advantage of that? Why is it good to have a slight fever when you're fighting an infection?
It makes the body non-habitable.
Kind of, yeah, and it increases metabolic rate, which makes the things move around faster, more resources, like our stores will be sent out, okay? So quicker enzymatic reaction, cells move faster, and it's achieved by the metabolic rate. Why don't we want then keep cranking it up? Why don't we want to just keep going? Because it'll move things even faster.
Cooks them.
Breaks down how?
I said cooks them.
Cooks them, yeah.
You need your
What does that mean? Denatures, that's what I was looking for, right? It changes, does it break down the molecules? Changes them how? Yeah, it forms and changes the shape of these molecules. They're not digesting them, right? It's not really breaking them down, but it's changing, permanent change, which is not good. So we don't want it too high. Okay? So that's when it happens about 42 or 108, so really it's not good. Even higher or closer to that is also going to cause some damage. You know, this is just starts shutting down. So next we're going to talk about our next branch called the adaptive, which is kind of like the third line of defense, right? So here it does take a little bit longer, okay? But when it does happen, it's much more efficient to get rid of our pathogen. So coordination of T cells and B cells. Which cell would you say is the coordinate? Which the HIV virus destroys? What T cells? A specific type of T cells. CD4, what's another name for those CD4 cells? Alpha T cells. Think of the 4, looks like a H maybe, if you just keep going down. It's the alpha T cells, right? So when this is targeted, these both affect in different ways, okay? So T cells, we call them cytotoxic, or it's cell mediated, while the B cells, we say it's humoral, right? Human, not joking, but liquid, right? We talk about aqueous humor, vitreous humor, liquid. So it's very specific towards an antigen, whereas up to this point, it's all non-specific. Yes, it has selections, right? For example, natural killer cells, they like only viruses and cancer cells. They do not like bacterial cells, but they'll try and kill any virus and bacteria cell. They try and kill any cancer cells, each natural killer cell. Here, each B cell, T cell can only attack one antigen, okay? Because they only have one type of receptor. So, the advantages are specificity. It's versatile, it can detect many different ones. There is memory, okay? And then if that's something that we want to be, it can result in tolerance. We'll talk a little bit about that. But memory and the specificity is very important, right? So we want it specific, and if the next time we encounter, we'll talk about this, it's easier to show with the antibodies. You can actually see the levels in terms of rate changes will neutralize in a second, right? So purpose is to either inactivate or destroy the pathogens, right? So it's by recognizing the antigens, okay? And it says lymphocyte activation. That's also what I'm talking about. First of all, where do T cells mature? Thymus gland, B cells. Bone marrow. So it's like graduating from college, graduating from high school, or wherever you went to training vocational school, but you haven't still got a job. Okay? That's kind of what's happening. these T cells. Their job is when they encounter the correct fit, correct job, if you will, right? And then they'll get activated. So, they have to be activated first. Okay, T cells have to be activated first, B cells have to be activated. So here I know it's talking about two things. So in here, if T cells, what needs to be activated? If it's first, it's talking about T helper cells, right? Once T helper cells activate, they can also activate B cells and other cytotoxic T cells as well. And in terms of activation, that means after this, they'll undergo two things. One, it's called cloning. What do you think is happening? Replication, yes, and producing the exact copy of it, right? So that way they can fight against that same antigen. Okay? They'll also transform whatever they have to do. Now they'll do their task, and it's very significant. The change is very dramatic in our B cells. I'll talk about that, right? So once activated, B cells become what's called the plasma cells. Their aim now is not to be activated here, just going to be producing antibodies. Okay? We looked at some antibodies. When did we talk about or look at antibodies? What typing, right? When do we produce antibodies, or when do we want to produce antibodies? To something that's not self, right? That we don't have. What happens if our immune system produces antibodies to something that is part of our body? What's that called? It's called immunity, right? Our own immune system producing antibodies against our own cells. So here, they will start producing the antibodies, T cells, B cells, they become called plasma cells. So here are the receptors. Right, here is a cell that's actually presenting the antigen, and they get activated. Here, it's looking different. Oh, these are destroying that cell. Right, the antigen, once it's been recognized, this cell, cytotoxic T cells, for example, will destroy that cell. So we need receptors. Okay. So on the T cells, we have T cell receptors, which are also need to be the special name major histocompatible complex. Yeah, there's two classes. So there are two classes of these receptors. They look like, I don't know if that image is very clear. Here, looks like almost a H, but with a little indentation. The indentation is for an antigen to be placed. Right? So class 1 is to be able to recognize first and foremost, is this a self or not self? While class 2 will recognize something wrong. So for example, our macrophages, right? What's the function of macrophages? To eat up. So it's eaten up this one bacterial cell, okay? But there's a possibility is many more of the same bacterial cells around the body. Okay, this macrophage can't find them all, so what they will do is take pieces of that macrophage of that pathogen and put it on its MCH. It's like almost like in the olden days when a king beheaded someone, they would put the head on a spike to kind of show. Right here, it's to activate our adaptive immune system. That way, now it's not just this pathogen, this macrophage looking for this pathogen. It's also these immune cells that can go around. There's B cells, T cells will go around the body. Remember we talked about when they're activated. Not only are they just activated, they will clone themselves. So you have hundreds more of that exact same cell which can recognize that antigen. And then they'll flow around trying to looking for those pathogens. Okay? So macrophages act as antigen presenting cells. They are going to present that antigen to our B cells, to our T cells to recognize and get activated. Okay. So let's talk about our T cells. There are 4 main ones. Okay. I think your book says suppressor T cells, the better one is regulatory T cells, it's the same, it says so, but just let me know, I think it was saying suppressor. This is the newer terminology used. So cytotoxic T cells, as this word name may suggest, it's going to destroy the cell. Okay? It's toxic to the cells. Okay? It's going to cause those holes in the membrane, and it's going to cause lysosomes to break out in that cell. Okay? What does T helper cell do? It activates cytotoxic T cells and B cells also. Okay, so we need those, which is what HIV can be dangerous because they will attack these cells, which means our adaptive both branches, cell mediated T cell, as well as humoral B cell branches are both affected. Okay? Regulatory basically says, okay, now I need more production of these T cells. When I have a lot, thousands of them, now I want you to scale it back, just wait, let's make sure we're balancing, because we don't want to use up too much of our resources, and also you want to overburn, right, because it produces heat. So they will regulate the activity. Hopefully what you'll understand what memory cells do. What do they do? So once activated, some will become the active cells, some become memory T or memory B cells too. Yeah, they remember previous exposures, and we'll talk about it. Next time the same pathogen comes in, they'll have a quicker response and a stronger response. Okay? Which is why we use that to stimulate for our vaccines, right? We're trying to produce memory T and memory B cells. So when we truly come across a pathogen, we are actually well equipped to fight that infection. So, in terms of T cells, that's our CD4, right? It is to activate cell mediated and the antibody mediated, right? They have to be activated by somebody presenting the MHC class. They can also coordinate non-specific. For example, they can trigger the complement system. Okay, they can also cause fever to rise as well, trying to fight infection. So they do play a role. It is more in us, but in terms of when you think about levels or layers, there are 3 layers. Cytotoxic T cells, they're killer T cells. They are cell mediated. These will destroy the cell. They produce a hole in the wall, as well as they'll cause lysosomes to break down. Okay. Apoptosis is cellular death, right? It is programmed cell death. So perforin is the one that drills the hole, also cause lysosomes to burst. What's another cell that did similarly? The natural killer cells, they're also lymphocytes, right? But they are non-specific, while cytotoxic T cells are specific. They're only doing one antigen. Each cell can only do one antigen. Like natural killer cells can do different antigens and stimulate by different things. They do have memory cells. T cells also have memory. Same with our B cells too. T helper cells, which we already talked about, also have memory. So these are called cell mediated, right? Because it's cellular attack. Right? And then regulatory or suppressor, they will dampen if it's too much. They will make sure that they keep going up if it's not enough. Okay? While memory T cells will enhance our reaction or activation next time. Okay? They can be both cytotoxic T cells as well as T helper cells. Then we'll look at how it does that. So B cells is called humoral or antibody mediated response. So here, these B cells, first they'll have the receptors, they will sense an antigen, they'll be activated, and then they'll start producing antibodies to that specific antigen. So sensitization and antigen activation. So it is immunoglobulin. We'll talk about that. If there's a question that asks what produces the antibodies, the correct answer will be plasma cells. Where do plasma cells come from? They are B cells, they're activated B cells, they're differentiated B cells. And then here too, as I mentioned, we do have B cell memory cells. Okay? So here, it will produce antibodies. Immunoglobulins are the protein molecules named. We have different types of immunoglobulins. Some of them are antibodies, some of them are receptors. So here is our immunoglobulin. First and foremost, what does it look like? Okay, I'm going to use 4 colors. Maybe. Yeah, let's use 4 colors. Yeah. Looks kind of like a Y shape, but a 2-pronged Y. Okay, so. So in this drawing, red and blue are one molecule, the orange and green are one molecule. There is different parts. We're going to talk about how one part is considered the constant part, which is going to be the red and orange, while this is what's going to be different. Okay, if these two molecules or part of these molecules are different, they will be able to attach different antigens. Does that make sense? Right? This is where antigens will bind. Okay? Antigen will bind here. So this is the antigen binding site of this immunoglobulin. Remember how we said it is different, it's specific? It's because this one is different in all different antibodies. Okay? Or immunoglobulins, which will also be receptors on cells. We'll talk about B cells, we'll talk about mast cells. So they have a pair, and I drew it one longer, right? 2 long ones and 2 short ones. So each immunoglobulin molecules made up of 2 long chains, heavy chains, 2 light chains. Okay, here they showed as purple and light purple, maybe, and blue and light. Okay, so the blue is the light chains, purple are the heavy chains. Okay, in them, at the tips of that white prongs, will be where the antigen will bind. Okay? It's because these can be different in each of the immunoglobulins that are produced that the antigens they bind are also different. Right? So it's specific. Okay, so that's called the variable M or variable segment. The other ones are the constant segments. Constant M's. So let's talk about the 5 different immunoglobulins. So here I'll expect us to be able to name them and also give me when we can find them or where we can find them. So we have 5. We'll start with IgM and IgG because these are the proper antibodies we're taking. Okay, IgM is the first antibody that's produced, while IgG is late or second response. Okay, and shape is also different. The IgM is a pentamer. What does that mean? 5. Okay, there are 5 of these immunoglobulins making 1 unit. I'm just going to do it as Y, not the whole. I'm not drawing the smaller portions. Bonded together, that's one unit. Okay, so they can actually bind, each immunoglobulin can bind 2 antigens. How many can this bind then? 10 antigens. Each immunoglobulin can bind 2. We have 5 of those molecules formed. 1. Okay, so this is during primary response to an infection. IgG, that's a monomer, quicker to produce later on, so it will be later because it can go in different phases, so it's late primary or a secondary response will have IgG. This is used in diagnosing acute hepatitis versus chronic hepatitis. Chronic hepatitis will see IgGs, while the acute, if you catch it early enough, will only show IgG. Okay? Any questions there? So all except 2 of these 5 immunoglobulins are monomers, just this Y shape. Okay? While 2 of them are different. One is the M, IgM is a pentamer. The next one's IgA, which is a dimer. Dimer is 2 of them. And this is also called the secretory immunoglobulin. So it's found in milk. It's found in mucosal lining. When there's antibodies, it's going to be this IgA that's found. Okay? Tears have them. Saliva has them too. Milk, to mother's milk, also has IgA, which is what they do recommend breastfeeding a child for newborn, right? Because our immune system is very immature when we're born. Yes, we have our first line, second line, that's pretty much it. We do not have that adaptive response. It takes about 8 weeks before we develop a decent response. Okay? So this is useful. Then IgE and IgD. IgE is one of those allergic responses. They will be found on a histamine producing or releasing cells. So on our basophils, right, we mentioned there histamine. When we release histamine, inflammation occurs. So these will be like receptors on basophils. Mast cells, these only have histamine. They're just floating around. Anything can trigger them, including eosinophils later on, they'll trigger mast cells. And when we have an allergic reaction, when we have anaphylaxis too, it's a lot of these mast cells just releasing all that histamine. Almost instantaneously. While IgD, these are the receptors on the B cell surface. Okay, so B cells are walking around. We call this IgD that's attached. Then when they're activated, they do not have that on the surface. They just start producing first IgM and then later on IgG. Okay? So IgD is a receptor that's found on B cells. B lymphocytes. Okay? Any questions? Next, let's talk about what happens when we have the antigen. What am my second response? Oh yes, I did show that first. So what happens? The antibodies themselves do not destroy the antigen. Okay? What happened in our blood grouping? What happened when we had the antigen and the antibody in the same plate? Agglutination. What does agglutination mean? Clumping. Just imagine. Antibodies, right? Really, it's not G. It's not M. It's G. But this binds one cell. This binds another cell, and another molecule binds that same cell. And we form this agglutination, this clumping effect. Okay? That's what agglutination is. Some of them, if they are toxins, these antigens. What is the definition of an antigen? Anything that triggers an immune response, triggers the adaptive response, right? Neutralization happens when there is a poison, think of it as a poison or toxin. This antibody binds to it because it's antibody bound. Now it's no more active, it's not got its active property, it's been neutralized. Okay, that only works for small chemicals which bind small into a slot of the antibodies. Then what was this complement system? So it's a cascade of proteins, right? If I had, for example, let's look at our red blood cells. Time for a few connections. Okay, so this will be like clumping. Do you recall what complement system was? It's a cascade of proteins resulting in what was the final result? Promotes inflammation, yeah, it does. That's only going to segregate these things. Like phagocytes, and also put a membrane attack complex, right? Now, it's going to put not just one each cell, it's going to put a number of them on the cell. Right? Extracellular fluid is going to go in, the cell will burst. Okay. That's when it activates, yes, it does. It does promote phagocytosis. If it's one little cell, that's great. If it's a clump, it doesn't really work. Yes, inflammation can stop this from spreading, but also puts in those membrane attack complexes. These holes in the membrane, holes that sledgehammer kind of like okay. This activation also can attract phagocytes, promote phagocytosis as well as inflammation by itself. Really complement all by itself. So let's talk about the primary response and the secondary response to that same antigen. Okay. So it roughly takes us about 7 days for the onset to a new antigen. 7, sometimes 10. Again, a good response. We start responding a little bit earlier, but it takes about, the peak is after 1 to 2 weeks. Okay? It does start later. So for example, it's easier to show you the B cell, how it changes, because you can see the number of antibodies change. Okay? So they will distribute plasma cells. What are plasma cells?
They produce antibodies.
They're the ones that produce antibodies. They're the activated B cells that produce antibodies. Okay? So, if you can give me your attention here. Okay? So this is a graph. This shows antibody concentration in blood as on the y-axis. This is showing time in weeks here. Okay? So, let's say 0, the first the day we got infected is day 0. Okay? It takes a few days, roughly about 4 days to really have any sort. I know this is not very enlarged, but it takes a little bit of time. It's not instantaneous. Okay? And then the antibody starts to increase. Peak is roughly between 1 to 2 weeks, so about 10 to 14 days. Okay? And then after every 4th infection will die down. Say now, this is day 0 for the second infection. Okay, second time this antibody and this antigen comes into our body. Okay, what can we see? First of all, yeah, it's very quick. Right, it doesn't wait as long for immune response. What else? The peak is even higher than this peak, right? And it's even sooner. It's not closer to 10 to 14. It's more like 5 or 6 weeks, right? It's less than 1 week here. 1 week would have been here, so it's just a little bit before. Where it really peaking high actually is at about a week, right? Another thing is it stays for longer. Here it's pretty much died down in 4 weeks. Here 8 weeks and still the antibiotic concentration is high. Another thing we can show in this graph, it also has a higher affinity to bind to those antigens. Like, oh, I know this antigen, let me find it. It has a higher affinity to bind them. So, quicker response. As you can see, stronger response. Okay, peaks also achieved much sooner. The numbers stay raised for a longer period of time, and greater affinity to those antigens. All of this is why the second response is a lot better, hence we try and stimulate that by our vaccines, right? We have different types of vaccines. We only had 2 types before COVID. Now we also have a third type. We'll talk about it. Okay, how we did use it, how we use it. So it's sensitizing and forming memory cells. So let's talk about immune responses, right? So we have what's called naturally acquired active, induced active, then naturally acquired passive, and then induced passive. Okay. 2 of these have memory, the other 2 do not. Okay. Which one do you think has memory? Naturally acquired. Yeah, it's the active. It's actually these 2. Both of these have memory. It's the active one that has memory. The passive one does not have memory. Okay? And we'll differentiate. So, naturally acquired active immunity, we are exposed to the pathogen. We fight the pathogen first time. Now we're able to have a stronger response the second time. Okay? Induced active, we are given the vaccine. The vaccine doesn't actually cause the disease. No, if you got an illness, flu-like symptoms, we'll talk about that. Sometimes we also get the flu just after we've got the flu vaccine. It's not from the vaccine itself. The bacteria or the virus was already in us. Okay? It had nothing to do with it because these vaccines that we give, let's leave COVID out of the same conversation for now. They were either what's called attenuated, live attenuated, which means yes, they can be metabolically active, but they cannot divide. They're not going to cause infections. Okay. Second one was they cut up pieces of them, dead pieces of them. It's like putting these bacteria into a blender, breaking the pieces, and then putting that piece into us. Right? It's like having the antigen. Now there's no cell. Okay. And then what was COVID vaccines? It was a little bit different. Yeah, it was the mRNA itself, right? It's called an mRNA vaccine. So where did we come across mRNA? Kind of in the nucleus. But in what conversation we talk about mRNA? Not replication. When we talk about replication, we're just producing DNA from DNA. Transcription. So what is the aim of transcription? And also next step. What was the next step after transcription? Translation. So we went from DNA to an mRNA. What happened in translation from mRNA? We made protein molecules, right? So if we just had that, and again, can produce protein molecules, but can that replicate? No, it doesn't have the capacity to replicate, so it can produce the proteins which our body will recognize as antigens. And that's what they were able to use that to So again, this cannot cause the infection, should not cause the infection, then it's not a proper vaccine, right? If it's a live virus, live one that can replicate, it's not a vaccine, that's an infection. Okay? But vaccines we alter it so they cannot replicate, either by killing it completely or making sure they cannot replicate at all, so that no one causes disease. Okay? So that's induced active. While naturally acquired passive immunity is from mother to child. Okay? Mother to fetus, mother to newborn. Okay? It's through the placenta, those immunoglobulins can cross. Through breast milk, immunoglobulins can cross. So that it lines the digestive tract of an individual in the line from milk, right? So that one does not have memory. Because it's just the immunoglobulin, she's not giving the memory cells. It's not inducing the immune response from the fetus or the child's immune system. Whereas when we talk about induced passive, it's like that antivenom. Okay, antivenom is basically antibodies against that specific toxin that we have. Okay. First time we treated COVID, right? What did we do? Somebody who had COVID infection, we got their blood donation, we removed the antibodies from that individual, and then we transfused to someone else. Okay? Did that someone else get better? Yes. Right? It helped because they had the antibodies. But did they have memory from this? No, they could get the infection again. Okay. So that's what we use. Also, we use that for many different illnesses too. Infusion of immunoglobulin infusion of this type of immunity. Yeah.
Would you consider COVID vaccine as an induced active immunity if you can keep getting it again?
Induced active immunity, you keep catching. So we keep catching COVID is because of different variants.
Or because you keep replicating?
Yeah, then we have to have new vaccines, that's first. And we can still get infection when we have active immunity, right? We just will respond quicker. So if it's there, if it's the same one, we'll respond quicker. We can still get infected, but the symptoms will be less. But if we have similar symptoms, it's probably different. It's most likely because we do not have immunity. Or it does weigh off. We found that there was about 50% immunity after a year. So yes, the immune response. Some memory is for longer, so you might have heard some vaccines are lifelong, right? Some are yearly, some are 5 yearly. For example, a tetanus shot is really valid for 10. It could be 5 depending on how the exposure was, what kind of environment you work in. Like if a big gas with a big corroded metal, they'll say, okay, you're 5, 6 years since, we'll give you another shot. Okay, just want to make sure. But if you just got a little scratch from a pin, you're 7 years in, they won't suggest you get a shot. So it's risk versus benefit. It can last up to 10 years, 5 we can give it again. Polio is considered lifelong. You have to introduce the vaccine. We've had the series ones. There is a series of that. Let's finish these two abnormalities. First is autoimmune, right? This is when our own immune system attacks our own cells. What are some diseases you might have heard of?
Lupus.
Lupus, so lupus erythematosus. It's also called systemic lupus erythematosus, SLE. What else?
Rheumatoid arthritis. Rheumatoid arthritis.
Rheumatoid arthritis, we talked about. Yeah, very good.
Celiac disease.
Celiac disease, yes. What about type of diabetes? Type 1 diabetes is autoimmune, right? Yeah. Do we know multiple sclerosis?
Yeah.
That's an autoimmune disease, right? That attacks what?
Muscle.
Myelin. Doesn't attack muscle, doesn't attack the nerves, but kind of there, right? It's the communication of the motor neurons to the skeleton. So here are a few, you guys sent a few others. Psoriasis is also another. Graves' disease is another one. Here, thyroid glands. They actually have hyperthyroidism, during Graves' disease, and then we have to destroy the thyroid either by taking it out or giving them radioactive iodine, which destroys it. Then on the opposite scale is immunodeficiency, right? Here it's also a problem. Here we do not have enough immune response. Okay. Two I'd like us to be aware of. This is they are both severely bad. One is called severely combined immunodeficiency disease or SID. This is what we're born with. Somebody could be born with it. They have infection after infection. Usually won't survive beyond teenage age because of multiple infections. Their immune system really doesn't work. Their adaptive immune system, they still have the first and second line, but their adaptive does not work. Right? They have cellular and cell-mediated immune problems. While acquired, AIDS stands for acquired immunodeficiency syndrome. It's not for autoimmune disease, right? Here, it's destroying the CD4, it's destroying T helper cells. Right? If T helper cells are destroyed, they are the coordinators of both cellular mediated and humoral, so both lines are affected. Can someone be HIV positive and not have AIDS?
Yes.
Yes, that's what we want, right? Previously it was a death sentence. Within 5-10 years max, they were dead. Okay? But now it's considered a chronic illness. We have good medications that will prevent the HIV virus from multiplying. We call it viral load. They'll keep checking to make sure the viral load is low. Okay? They also check at the same time they usually do the CD4 count too. If the viral load is high and the CD4 count starts decreasing, we start to get concerned. When it reaches a certain number, it's when we call it AIDS. Very, very carefully monitoring and very aggressively treating them. Okay? And then usually they do succumb to the disease. A couple of years is usually maximum after they develop AIDS. Whereas nowadays you can live 40, 50 years with HIV positive and not develop AIDS because you've got good medications. Okay. So HIV stands for human immunodeficiency virus. Causes a deficiency in the immune system. The next problem is allergies. Right here, what are allergies?
When your body reacts to something that is introduced to it and causes them to release more histamines.
Yeah, so it's going to cause an immune response. So here they're called allergens, right? Because they don't cause infection. They're not toxic to our body, but our body thinks of them as being toxic. Okay? They somehow don't like, for example, pollen. They're allergic to peanuts. They don't like the chemicals in that, honey, right? They just recognize as that being a foreign invader. Really, it's not to our body. Okay, so allergic response are inappropriate, excessive immune response to things that are called allergens. Something that can really should sensitize immune responses. We categorize them by how quickly they do react. We say immediate hypersensitivity. That's when the response is straight away, right? You're used with the allergen, the response is straight away. By the way, is it the first time that they're exposed, they get that allergic reaction, anaphylaxis? No, it's subsequent. They have to be at least twice introduced before they show signs of it, right? You might have heard of anaphylaxis and then anaphylaxis shock. Anaphylaxis is widespread, right? Seasonal allergies, usually restricted to our upper respiratory, right? Anaphylaxis throughout our body, vasodilatation, and if tissue perfusion decrease, that's inadequate, we call it a shock, right? So here it's excessive vasodilatation, fall in blood pressure, and then collapse. What are some treatments of anaphylaxis and anaphylactic shock? We'll talk about one additional things we do. EpiPen, right? What does EpiPen do? Or the contents of EpiPen do?
Vasoconstrictor.
Vasoconstriction is part of what in our nervous system? sympathetic, right? Sympathetic causes vasoconstriction. Right? What else is, we'll talk about shock treatment as a part of EMG, right? Those individuals lose heat very quickly, okay? We'll try and get back that blood pressure, but also make sure that the body temperature doesn't drop. Because one of that is warming the body as well as part. Okay? Let's go try to maintain blood pressure with medications. Then next one is called cytotoxic or type 2. This is what's seen with incompatible blood transfusions. What's another very severe complication, possible complication of incompatible blood transfusion?
Like rejection, right? Is it rejection?
That's transplant.
Okay.
Here I'm talking about blood transfusion, right? Something called DIC. What does it stand for? We talk about it. Disseminated intravascular coagulopathy. What's happening here? Clotting and bleeding the same person. Type 3, this is when those complexes goes and lodges itself. For example, you may hear of post-streptococcal glomerular nephritis. This is a type 3. These are the antigen bound with the antibodies floating around, it goes in the blood everywhere, it gets clogged into the glomerulus, which we'll talk about what affects that too. Well, delayed, it takes roughly about a week, right? You may have experienced it if you came across poison ivy. The peak is days after. It's roughly about a week, 5 to 7 days after is when we actually will see symptoms of it, right? You'll have those rash, but I think that's twice a week. Oh, by the way, this is very common, and my colleague had this, and she did not realize what it was. Yes, even though you didn't touch it, if you have pets, just think about where they have what was happening to the feet. Could not understand why she was getting this.
That the same thing happened to me. My dog was rolling it and I couldn't figure out why I was getting it.
Yeah, that's where it came from. I don't know, you might not be directly exposed, they just bring the oil, get the oil from that, from those things, so it transferred to the dog's fur, and then was rubbing on her face and her arms, and it was all rash. She couldn't figure out where it came from. And looking at it, it was just like thousand. Then feed her dog sleeps. Questions? Let's take a break, and then we'll do a little bit of our next chapter. The main part of it will be